Hey, this is Jack Jackson. In this video, we're going to be talking about inverse relations. So in general, a relation is a set of ordered pairs, and that can be represented many different ways, as arrow diagrams, as tables, as graphs of things, especially if they're ordered pairs of real numbers. An inverse relation of a given relation is found by simply switching all the coordinates of the ordered pairs. So, for example, if we have a table here, um, like this, here's the table for the inverse relation. So notice that you have a preimage here 3, 2, its image is 2, 3. If the preimage is 8, 3, its image is over here at 3, 8. So you're just switching all the ordered pairs. Okay, and then if you do it as an arrow diagram, those arrows reverse. Okay, so you have 3 going to 2, 4 going to 5, -2 going to 8. You just reverse the arrows. 2 goes to 3, 5 goes to 4, and 8 goes to -2. So that means that the domain and range are just going to swap places with each other. Okay. Now, if it's a rule, sometimes we give a relation by a rule. If a relation is, say, take 2 steps forward, the inverse relation is to take 2 steps backward. Consider a relation where the first coordinate is the mother of the second coordinate. The inverse relation is a set of ordered pairs where the second coordinate is the mother of the first coordinate. Or in other words, where the first coordinate has as a mother the second coordinate. If the original function takes the day as the input and gives the high temperature as the output, then the inverse relation reverses this by taking the high temperature as the input and gives the day as an output. If we think of a relation as a factory or process involving a series of steps that transforms the input into the output, then the inverse relation simply reverses the process. This process is reversed with each worker undoing what he previously did, so that the inverse process involves exactly the opposite steps in the opposite order. So suppose a relation is given as an assembly process involving 3 workers. The first worker attaches part A to part B. The second worker screws part C to part B. Finally, the third worker packages the assembly into a box. Well, what would be the inverse relation? It's the opposite disassembly process. To undo what's been done in the original assembly, the inverse relation, each worker must do the opposite of what he did in the assembly process, the original relation. And they have to do it in opposite order. So the input for the inverse relation is the boxed assembly. The first thing that must happen in this disassembly is to have worker 3 remove the assembly from the box. Then worker 2 unscrews part C from part B, and finally worker 1 detaches part A from part B. Notice that each step is reversed and the opposite order of steps is used. If the original relation is to add 1, then multiply by 2, the inverse relation is to first divide by 2 and then subtract 1. So the original relation is y equals 2 times x plus 1. So x plus 1 is in parentheses, so you add 1, then you multiply by 2. The inverse relation is take x divided by 2 and subtract 1 and let that be y. So what would that mean in terms of a relation, in terms of order of equation? So if you have an equation with, say, 2 variables like x and y, with x being the first coordinate, y the second, as we generally do, we just simply reverse the ordered pairs, replace x by y and y by x. So if the original relation is y equals x cubed, the inverse relation is x equals y cubed. Now notice in this case we can solve for y in a single equation. Y is x to the 1/3 power, or in other words, the cube root of x. If the original relation is y equals x squared, then we get x equals y squared for the inverse relation. Notice you cannot solve that one for y in one single equation. It takes 2, y equals the square root of x, or y equals the negative square root of x. If the original relation is y equals 2x minus 7, the inverse relation is x equals 2y minus 7. And there you can solve for y by adding 7 and dividing by 2 to get y as 1/2 times parentheses x plus 7. Or if you'd like to distribute that, that equals 1/2 times x plus 7/2. If the original relation is y equals 2 to the x power, the inverse is x equals 2 to the y power. if the original relation is x over 4 squared plus y over 5 squared equals 1, the inverse relation would have y over 4 squared plus x over 5 squared equals 1. Just replace that x by y and that y by x. Okay, so why are we even talking about this in this particular playlist on reflections? Well, it's because inverse relations are a particular reflection of the original relation. Okay, so here are the same ones that we have here. Y equals x cubed. The original is in blue here, and x equals y cubed, or y equals cube root of x, is the red one. If you notice, they are reflections of each other about the line y equals x. Notice that the fixed points there of 0, 0, 1, 1, negative 1, negative 1 are on the mirror line, so points on the mirror line are fixed, and you see this reflection. So this happens, you can always do this for any relation. Here's another one. Here's y equals x squared in blue is the preimage. The image set is the x equals y squared here. Notice that the original function here, original relation is a function. It passes a vertical line test, and vertical lines flipped over the mirror reflection over the line y equals x become horizontal lines. So the blue one has no repeats in the first coordinate, or in other words, it passes a vertical line test. The red one will have, the inverse relation will have no repeats in the second um, um, coordinate. It will have passed the horizontal line test. But notice it, since the original one did not pass the horizontal line test, it was not one-to-one. The red one is not a function here. Here we have two lines. These were the two lines that we had up here. Y equals 2x minus 7 and x equals 2y minus 7. Those are the two lines there. Again, a reflection over this sort of green line here in the middle, y equals x. They both happen to cross each other on the on that line. Here's our exponential. Y equals 2 to the x, and here's x equals 2 to the y. If you solve that for y, it's y equals logarithm base 2 of x. So a logarithm is a reflection of an exponential over that line, y equals x. Here are two ellipses that we had in the last one. The original one, x over 4 squared plus y over 5 squared equals 1. That one is the, let's see which one, that's the blue one. And you reflect over this line y equals x, you get the red one here. Now, can we prove that this is what's happening? And yeah, we can prove that. So I'm going to leave the details of the proof to you, but I'm going to give you a hint. So what we've got is a relation. Here's an illustration of the x cube and the y equals x cube and x equals y cube example. But it could be any example here. We take a point AB, you know its image is BA. Well, what does it mean to be a reflection? Remember, to be a reflection, this line connecting preimage to image has to be perpendicularly bisected by the mirror line. So we can use the slope and midpoint formulas to help us. To show that this is the midpoint, we just have to take the point AB and BA, use the midpoint formula, and show that that point is on a line where the x and y coordinates are the same. Secondly, we know that this line y equals x has a slope of 1. If we could just show that this has a slope of negative 1, no matter where we are here on this, when we take an AB and replace it by BA, the line going through those two, if we can just show that that has a slope of negative 1, use the slope formula, the product of the slopes are negative 1, or they're negative reciprocals of each other, and that's enough to make the lines perpendicular. So I pretty much talked you through the whole proof, and you can write down the details of that. So if we've got a graph here of any relation, you know, a smiley face, anything that we want to draw, and it's on a grid, if we can actually find its inverse relation, at least the graph of it, by just reflecting over that line, perhaps using tracing paper, perhaps using the grid itself, perhaps using GeoGebra, but not necessarily having to know the formulas. We can do that. Or if we know the formulas, we know how to do it as well. Now notice that neither the relation nor its inverse had to be a function. So every relation has an inverse relation. Okay, so which relations are invertible? Well, all of them are. Which functions are invertible? Well, really all of them have an inverse function. But sometimes you'll see that question in like a college algebra book and say, which functions are invertible? Well, they don't mean really the question, does it have an inverse? They mean, does it have an inverse, which is a function? In other words, they want a relation to be a function to begin with and its inverse to be a function as well. So the question is, when would that happen? Well, consider the relation to be a function. For the original, it has to pass the vertical line test, okay, and which will mean that the inverse passes the horizontal line test. But similarly, if the inverse relation is to be a function, it's got to pass the vertical line test, which meant your original relation had to pass the horizontal line test. So both of them pass both the um, vertical and horizontal line test. Therefore, they both have to be one-to-one functions. So which ones have, or which kinds of relations are both the original and its inverse functions? And the answer is one-to-one or injective functions. Okay, so how can we achieve this graphically and algebraically and numerically when we have some relations? So for example, if you have y equals x squared, if we want to reflect over the line y equals x, that's going to give us the inverse relation. You replace y by x and x by y. And if you want to solve for y, you can. Of course, in this one, you can't do it in a single equation. But here we've worked it out, again, not just any table for both of these, but I've sort of picked sort of an organized table here with some usual suspects there for the x coordinates, worked out what the y is by the formula. But then to get the table for the inverse relation, I'm just swapping the points, right? So instead of -2, 4, we get 4, -2. Okay, and so that's going to be those reflected over that line y equals x. Okay, what about y equals x cubed? Again, take some usual things here, cube them to get the y's. Then just take each one of these and reverse the coordinates. -3, -27 becomes -27, -3, and so forth. So these 3 points right here end up getting fixed, but the rest of them get moved around. The 3 points that are fixed are on the mirror line, y equals x. And there we get the two graphs are reflections of each other. Okay, so that is a special kind of reflection that turns out to be a really important thing in algebra, is the idea of an inverse relation.